Good afternoon again. We ended the last session with a short view of the single sampling plan. In fact, that plan is still showing on the screen there. I take a lot of size big N. I sample n items out of it, which is of lot quality P, which is an unknown quantity, and I inspect all the items there, and the number of defects turn out to be D, and then I compare that number of items found defective, that little d to be, I compare that to this control number called C. If d is less than or equal to C, I accept the lot, otherwise I reject the lot. Now in doing that, if you remember, I had it on my table here, and I utilized what we called a little formula which came from the binomial distribution. Now I'm going to actually give you this formula there so that you will have a pretty decent idea of how to utilize the binomial distribution. Now if lot quality, if this is taken to be P, that is P is the fraction defective in the lot, then suppose I pick n items. The probability that I'll find d defectives in n items that I pick out of this, when overall lot quality is P, this turns out to be a binomial distribution, and that goes like this. This probability is equal to n choose d, p to the power d, 1 minus p to the power n minus d. And this formula tells you that, this is the exact formula that tells you if n items were chosen, if they were inspected and d defectives were found, when p is the overall defect level of the lot, then this is the expression that will give you the quantity P or PA, or the probability of finding d defectives in n items. And here of course let's write the range of d. D can be as small as 0, it can be 1, 2 and so on, and it can be at most be equal to n. This is the range of this, and this particular distribution is called the binomial distribution. Couple of assumptions here. One is that n is very large. That's like 1. It's a very big assumption there, and sometimes lots are pretty big. In fact, it turns out if your sample size and lot size, if the ratio of, if this little n is 1/10 of this, you can apply this formula there. There is no problem there. A lot of sampling plans have been designed based on this, and I'm going to be showing a use of this particular formula in designing a single sampling plan. I'll do that. Let's first take a look at something called the OC curve, the operating characteristic curve of the plan. Now notice in the recall that when I drew the single sampling plan and I had this item there, I had this particular item there, the quantity that I was most interested in was this probability, the probability of accepting the lot. That's what I had a lot of interest in. I had a lot of interest in this because this is the probability of accepting the lot which is at quality level P. So this is a very important quantity. I really need to really have a good feel for this. Now if P changes, if little p changes, PA also will change because that will be determined by this formula there. As I change P, PA is going to change. PA is the chance of accepting the lot, the probability of accepting the lot. Now there must be a relationship between this little p and PA, and that is shown by the OC curve. Let's take a look at this curve there. What is this curve called the OC curve? It is the graph of the percent defective P in a lot of batch versus the probability that the sampling plan will accept the lot, which is PA. So in fact it's a plot between PA, big PA and little p. That's what this plot is. That is what the OC curve is. And this is determined on this is all really dependent on the sampling plan, the particular sampling plan you are using. That's going to determine the relationship between little p and PA. In fact, what you'd like is you'd like the sampling plan in such a way that this PA is high when your lot quality P is very near AQL. And also you'd like this PA to be small as possible when this lot quality is near RQL. These are the two considerations that you must have. In fact, the more the plan is able to reject lots at the RQL level, the more discriminating it is. It should accept most of the lots which are at AQL level. It should reject lots which are generally around RQL level. Then I'll say it's a good plan. Now, to get an idea whether the plan is good or bad, we need to look at the OC curve of the plan. And I'm going to show you what that OC curve really shows you. Here's the picture of the OC curve of a typical sampling plan. Let's look at the axis first. On the x-axis, I've got lot quality, which is little p. Little p is on the x-axis. And on the y-axis, I've got PA. PA is the probability of accepting the lot, that is big PA. Big PA goes this way. Now notice something. I as a user of the sampling plan, I would like to have, when my lot quality is near AQL, and let's pretend here that AQL is 3%. If AQL is 3%, I'd like to have a high PA at this point. I'd like to have a high PA. And the curve shows here that this particular, some sampling plan for which this plot has been drawn, it will accept 90% of the lots which are submitted with your little p at 3% level. Now, the same plan will accept a very small number, only 10% of the lots when your lot quality little p becomes 10%. So, like if RQL is 10%, then only 10% of the lots would be accepted by the sampling plan. Now, what happens in between? You see this sloping curve there? There's a formula for it. I'm going to show you what that formula is like. That formula gives you, for any value of P, it will give you the corresponding value of PA. So what does the OC curve shows you? What does it show you? It shows you the chance of accepting a lot at the RQL level. It's also showing you the chance of rejecting a lot when the lot really is at the AQL level. And it also shows you the fate of all the lots which are at quality levels which are between AQL and RQL. That's what the OC curve does. So the OC curve actually is a pretty useful piece of curve. It's a pretty useful device. And this can be drawn exactly. And I'm going to show you the method for drawing this exactly. So again, let's come back and look at some of the terms there. Acceptable quality level is the percent of defectives that the customer is willing to live with forever, because that level of defect in the incoming lots is okay with him. Then there is, of course, this other idea called LTPD or RQL. It is the upper limit on the percent of defects that the customer is willing to accept. Customer is willing to accept, but only with a very small probability. Then there is some other term called AOQ, average outgoing quality. I'm going to show you what that quantity is. And of course, there is a limit on that AOQ also, which is called AOQL. And that also I'm going to show you what these are. So in fact, we know what AQL is. We know what LTPD or RQL is. They are the same terms. And I'm going to explain to you what AOQ is and what AOQL is. These I'm going to show to you. Now, what about an ideal curve? Ideally speaking, of course, you'd like to reject as many lots at near the RQL level as possible. You'd like to reject as many lots as possible which are at quality level, that is near RQL. And you'd like to accept any lot that is coming at or better than what we call the AQL level. So in fact, at AQL level, my PA is the probability of acceptance. It should be very close to 1. And at RQL level, my probability of acceptance should be very close to 0. This is the ideal curve. Now think for a minute. I could have a sampling plan that will operate actually in this ideal mode provided I did 100% inspection and I made no inspection errors. I committed no inspection errors. If I was able to do that, I'd be able to operate pretty comfortably, because I'll be accepting all the lots which are acceptable and I'll be rejecting all the lots which should be rejected. That I should be able to do. But what happens in real life? In real life, I'm not doing 100% inspection. So my real plan is going to be either like this. This is the real OC curve of a plan that I use, or it could be like this, the black curve there. So either the red curve or the black curve, this is what reality is going to be like. What is the difference between these two? It turns out that the black curve will reject most of the lots that are at poor quality level. It will accept almost all the lots which are at AQL level. AQL being 3%. And RQL being around here, it will reject most of the lots which are in this area. Now look at the red curve there. This is another sampling plan. It's got the OC curve of that plan there, the red one. It is not as discriminating. It is not able to separate between good and bad lots as effectively as the black curve. In fact, the ideal plan would be like you go down just a little bit, then you come all the way vertically down, then you go out this way. That was the ideal curve, and the black curve approaches it. So the black curve is better than, the black sampling plan is better than the red dotted sampling plan. Now, what are the things that are of interest to the producer? The producer would like to make sure that the sampling plan accepts as many lots as possible which are submitted at the AQL level. And what is it that the consumers would like to do? The consumer would like to have the sampling plan reject as many lots as possible which arrive at RQL level. Now, once you set up your sampling procedure, you basically take these rules and you give the gauge, to the inspector, and you tell him now you operate any lots that are arriving by trucks, by boxes and so on and so forth. You utilize my sampling rule, and my sampling rule is what? Pick little n items, and I'm also going to give you this control number C. Look up the number of defectives found in those n items. If the number of defectives found exceeds C, reject the lot. If the number of defectives found in the little n items which you've inspected, because now this is the sample and you must inspect every item in the sample. If that number D is less than or equal to C, accept the lot. This is all right for my production. This is what you'd like to be able to do. Obviously, the producer would like you to accept as many lots as possible. They would like to make sure that your PA at the AQL level should be pretty close to 1, and the consumers would like to make sure that the PA at the RQL level is as close to 0 as possible. This is like something that is desired by the two parties which are forming the two ends of the supply chain. So in fact, in general, look at alpha and look at beta now. Beta is the probability of my accepting a lot which is at LTPD or RQL level. Beta is the chance of the sampling plan accepting a lot which is at RQL or LTPD level. That's supposed to be quite small. It's kept generally around not more than 10%. And alpha is the chance of my rejecting a lot, which is like 1 minus PA at this point, 1 minus PA at this point, that is equal to alpha. That is the probability of my rejecting a lot which is otherwise at AQL level. At this level, ideally I should be accepting all the lots, but I reject an alpha fraction of the lots. This alpha and this beta, these are the contentions. These are actually the ones that we have to balance. So there are these two types of risks involved: wrongful rejection and the fraction of items, fraction of lots that I reject at the AQL level, that is equal to alpha, and wrongful acceptance of poor lots. Poor lots are of quality RQL. That quantity is supposed to be beta. I should not exceed alpha in rejecting good lots, and I should not exceed beta in accepting what we call bad lots, which are bad lots are near RQL level. And a curve like this is not very discriminating. It will probably allow a lot of bad lots also to come into the system. The ideal curve is like this, which stays near 1, near AQL, and it immediately falls to the ground and it rejects every lot that is slightly different from your AQL level. Therefore, there is actually there is some reason for us to take plans which are here and to try to make sure these plans approach this ideal plot. This is what we'd like to be able to do. So, we'd like to design sampling plans. This is like a particular sampling plan. This is not very discriminating. What we'd like to be able to do is, we'd like to design a sampling plan in such a way that this plan is as close to this ideal shape as possible. Let's see how we do that. This is again a continuation of the same thing. Bad lots definitely are at this end and good lots are at this end. That's what they are. In between, of course, there are lots that we accepted because I'm not doing 100% inspection. And I would like to make sure that this curve approaches the ideal curve as much as possible. This is what I'd like to be able to do. Now, there are ways to calculate these numbers there. There are ways to calculate these different numbers. And those would be using the, remember the binomial formula that I had there? The binomial formula is shown right here. This is the binomial formula. This PA equal to summation d equal to 0 to c n choose d p to the power d 1 minus p to the power n minus d. This is the formula that gives me PA. And with the help of this, by plugging in different values of P, I can determine the values of PA and I can produce a plot. The plot looks like the plot that I've got on the screen here. This plot can be plotted once I have my binomial formula with me. Now, sometimes what happens that the lot supplied is of finite size, like for example a truck or a bus. In that case, we use a distribution that is the hypergeometric distribution, not the binomial distribution. We use the binomial distribution when the lot size is so large that I can pretend that big N is too large when I compare that to little n, and I can use the binomial distribution. I should be able to use this binomial distribution which is here when lot size is quite large. But if lot size itself, that big N there, if this big N is not too large, I have to use what we call the hypergeometric distribution. And in that case, I'll be using the type A OC curves. It's also possible for me, instead of using the binomial distribution, I may be able to use the Poisson distribution also, and the formula is shown here. PR is now the probability, and I'm going to be drawing that for you. PR is the probability, and if I draw it correctly using the Poisson distribution, the Poisson formula goes like this. First of all, there being R defectives, this is equal to NP raised to the power R E minus NP divided by R factorial. This is the formula for finding exactly R defectives when I sample from an item which has got N, and P is the overall quality of that lot there. N items have been sampled from it in which R defectives have been found. P is the overall quality of the lot that is supplying those parts there. Now, what have I got there? A couple of things have happened here. One is I've made a decision now. I've made a decision here to select a sample size of N. So, sample size is N and lot quality is P. These two are given to me. If these two are given to me, then the Poisson formula gives me the chance of finding R defects in N items chosen. This is the formula which I can also use in designing a sampling plan, or in fact in constructing the PA, the PA number, the PA formula. How will I find PA? Suppose my rule is that you accept the lot. PA is the probability of my finding D less than or equal to C. If I use the Poisson formula, this will turn out to be D equal to 0 to C NP to the power D divided by D factorial E minus NP. This is the formula. This is the formula I'll be using if I have to construct an OC curve that uses the Poisson formula as the basis. Now, this is an alternative to the binomial distribution. So, in fact, there are several ways I could construct this OC curve. I could use the binomial distribution, which is this formula. Remember this formula there, this is the binomial distribution, or I could use the Poisson distribution. I could use the Poisson distribution, whichever is convenient for me for doing the calculations, I could use that. And by chance, if it turns out that my sample size is what it is supposed to be, which is little n, but my lot size is finite. My lot size is my n is my lot size, and this n is not too large. In that case, I'll be using the hypergeometric distribution. And there the formula is given by this. And again, I can work out the exact formula for PA, the probability of accepting the lot. Now, this again is given in your slides. As we go down, you'll be able to see this one. And we'll come back and we'll use this. In a couple of minutes, we'll be using this. Let's carry on with our distribution there. We were using the Poisson distribution, so we got the Poisson formula there. And with Poisson formula, I can actually work out my PA. PA, remember, PA is the y-axis. PA turns out to be y-axis in the OC curve, and the x-axis in that case turns out to be our lot quality P. Lot quality P is here and PA is there. And what I end up with for a given n and a given value of P, I end up with this OC curve there. What does the OC curve tell us? It tells us the risk of accepting a bad lot or the risk of rejecting a good lot. Rejecting as a good lot is something that the supplier is going to be upset with, and accepting a bad lot is something that the user is going to be upset with. And both of these we have to balance, both of these we have to minimize. Generally speaking, the considerations are economic. Like I said to you earlier, we need not always worry about the binomial distribution as the only way. We may be able to use the hypergeometric formula, or we may be able to utilize the binomial formula also. Hypergeometric, Poisson, or binomial, these are three popular formulas which are utilized in trying to draw the OC curve in most cases. The ideal OC curve, of course, is like this. It just starts out, it accepts everything that is near AQL, and it rejects everything that is beyond AQL. And this would be the situation. I can guarantee this, provided I take the full lot. I take the full lot and I inspect each and every item. I take the full lot and I inspect every item so that I can pull out any defectives that might be there. I pull out all the defectives and end up with only good parts there. If I would do that, I could operate in a way that would be pretty close to what we call the ideal curve that we could do. Now, let's see how we balance the two risks. Now, AQL is something that the supplier knows. AQL is something that the consumer is willing to live with forever and ever. And therefore, the consumer is interested in making sure that he gets generally items which are near AQL level. Occasionally, if he does get something that is near the RQL level, the consumer would like to make sure that lots coming at near the RQL level, those are rejected. The producer, on the other hand, he also knows that AQL is a quality level that is acceptable to the consumer, to the user or the consumer. Therefore, what the producer would like to make sure is that any lot that is submitted at AQL level of overall quality, it is accepted by the customer. Now the decision to accept or reject the lot, that is based on the NC sampling plan that I have in the single sampling case. Therefore, we got to make sure when we design a sampling plan, we do it in such a way that we take care of the interest of the user and also the interest of the supplier. Both of those interests, they have to be brought together. And there's an easy way to do this. It's surprisingly easy. They might appear to be conflicting, but I'll show you a process by which you'll really see it's not that difficult to work this out. This is of course the binomial formula, and it's just showing you that if you use the binomial formula, you can construct the OC curve by changing the value of P given a value of N and given a value of C. If you change the little value of this little p there, you can determine the different values of PA that will be generated from this, and then you can plot P versus PA, which is actually the trace of the OC curve itself for any N, for any sample size and any control number C that is given to you. So in fact, it is the same manner in which this OC curve has been generated. It's not very difficult to do. And of course, the ideal curve also I showed you. The ideal curve is valid only when you are doing 100% inspection. It is not valid otherwise. That's something we'd like to be able to do. Now, you know, there are curves. There are various types of curves possible. Let me draw a few curves here for you. I'm going to be using this paper here, and I'm going to be drawing the two axes there. One axis is P. P is the overall quality, and this side I've got PA. P is the chance of accepting the lot. The ideal curve, of course, is it's going to start at 1.0. It's going to come down to RQL, AQL level, and from that point on it's going to stay right there near 0 and all the way beyond this. RQL is here. This is like an ideal OC curve, but generally what happens here, OC curves, they behave like this. Another curve, it may behave like this. A third curve, it may behave like this. Now, obviously, look at these curves a little carefully. Look at the value of beta. Let's say RQL is here. Beta here is quite small, but beta here is somewhat larger, and the beta for this curve is quite large. Now, what is beta? Beta provides the user or the consumer the protection. So if large beta is there, the consumer is not going to be protected very well. And look at alpha now. Alpha is small here. Alpha is protection provided to the supplier. Then I've got alpha here, which is slightly larger, and this one has got the largest alpha. The larger is the alpha, the larger is the supplier's risk or the producer's risk. So in fact, what the producer would like to do is, he would like to have as small alpha as possible. Alpha be small. This is what the producer would like to be able to do. And what is it that the consumer would like? The consumer would like beta to be small. This is what the user would like to be able to do, or the producer would like to be able to do. There is the consumer would like to be able to do. So the consumer looks at this end and the producer looks at this end. What we would like to be able to do is, we would like to set some target here. I would like to set some target here. I would like to see, can we construct a curve that goes through these 2 points, this point and this point. Can we do that? This is something that we would like to attempt now. Let's go to the screen there. Notice here what happens if I vary these curves. If I change n, if I change n, little n is the sample size. As sample size is increased, the OC curve becomes more and more discriminating. So it moves this way, which is like it becomes better and better from the perspective of, here we've got RQL, and the guy who is most concerned with this is the consumer. So it's better for the consumer to take a large sample. Remember this now. It's better for the consumer to use large sample in sampling. And now what about the other story there? If I increase my C, the curve tends to rise, and when the curve rises, what happens to alpha? Look at what happens to alpha. Alpha becomes smaller and smaller. When alpha becomes smaller, the producer's risk goes down. The producer's risk was high here, it became quite small there. On the other hand, the consumer's risk was low here, and it got to a point which is like more than zero, definitely. So in fact, what we have to do is we have to find a compromise between sample size and this control number C in such a way that I'm able to provide a protection to here the supplier or the producer and the consumer, who is the user of these items which are arriving by lots. Let's see how we do that. We have some general definitions here. In fact, these again define AQL and RQL for us. AQL are put in green and RQL or LTPD are put in red here. And these are two curves now. They are both actually for finite size lots. They are both for finite size lots. If I look at an infinite size lots, which happens sometimes when the supply is such that the truck size is very large, or I've got continuous production feeding my factory, continuous production by the supplier feeding my factory, then of course the supplier's lot size is very, very large, and I could be using the type B curve there. Now these are only to indicate to you that as far as large lots are concerned, there is not that much difference in the OC curve. Let's take a look at whether to use the Poisson distribution or some other distribution. If lot size is large, use the binomial distribution or the Poisson distribution. If lot size is small, use the binomial distribution, use the hypergeometric distribution. And let's try to do a small problem. Let's try to work out a very, very small problem. Pretty simple problem there. And what we would like to do is, you see the problem that is indicated right at the bottom? A lot of 20 tires containing 5 defective items. 5 defective would lead to basically P being 25% defective. Those are supplied to you. If an inspector randomly samples 4 items out of the 20 tires, what is the probability of finding 3 defective ones? This exercise basically is a direct application of this formula there, the hypergeometric formula. Let's see how we do that. I'm going to be doing this. I'm looking for the probability of 3 defectives. So I'll write this P, 3 defectives. And these 3 defectives are in 4 items. This should be equal to, now look at the formula given there, n minus r divided by n minus r, choose n minus m. Let's try to write that here. The first thing I would like to do is, I would like to make sure that I account for the number of items which are picked out of the lot. The lot size here is 20. So I put 20 there, and sample size is 5. Sample size in this case is 4 items only, so 4 is there. Now this is the total number of combinations, different number of ways I could construct samples of size 4 picking out of 20 items. 20 items are basically the size of the lot. Now let's take a look at the number of defectives. In the original lot, which consists of 20 tires, there are 5 defective tires. And I would like to have 3 defective tires appear in the hands of the inspector. So 5 choose 3 is the number of different ways 3 defectives could be picked out of 5 defectives which are present in the lot itself. Then what about the items which are not defective? Those are 20 minus 5, that is equal to 15. And then what is the remaining number? It turns out that if I pick 4 items, if I pick four tires and 3 are defective, there is only going to be one that is going to be okay, one good one. This is the probability now of my finding 3 defective tires when I choose 4 tires out of a lot of 20, which has got a total of 5 defective items in them. This has been done using the hypergeometric distribution. And this is a very important formula which you use whenever we've got finite size lots. Whenever we've got finite size lots, we would like to use the hypergeometric distribution. Okay, let's get back to the curves here again. These are a couple of other curves that I show here to give you an idea that OC curves are never the same. OC curves depend a lot on whether the lot is finite or the lot is infinite size, and also if there are items which are like the number of defectives that I allow to be in the lot, in the sample, which is the control number C. If C changes, the OC curve will change. If lot size changes, big N changes, the curves will change, the OC curve will change. And of course, if sample size N changes, little n changes, then again the OC curves will change. So the OC curves depend on all of these properties. And of course, the OC curves tell us whether a plan that I make, my plan is always going to be an NC plan. Remember, basically any kind of plan that I work out, whether it's a single sampling plan or a double sampling plan, anytime I've got a plan worked out, that plan is going to be such that I end up with protection provided to the user, and also I protect the supplier. The user should not end up with a lot of defective items, and the supplier should not end up with a lot of lots returned to him which are otherwise at AQL quality level or near AQL quality level. To do that, we obviously have to optimally design the sampling plan. This is like one other item that I should mention to you. You might reject the lot, but it's very possible when you reject the lot, you would not want to return it to the supplier. What you'd like to do is, you'd like to probably charge him for the defective items, but you'd like to sort the lot by doing 100% inspection, remove the defective items, and make sure you can carry on with your production, because your stoppage of production can be more expensive than returning the lot and getting replacements and so on and so forth. So what you'd like to do most of the time is you'd like to do rectification. You look at the defective lots, ones that have been rejected by your inspection procedure, by your acceptance sampling procedure, and sort out the good items from the bad items. Take the bad items, replace them with good items. Now you've got supplies now that can carry through your production. So actually now you've got parts that you can utilize in your production process. Meanwhile, of course, you'll negotiate the deal with your supplier as to what to do with the defective part. Should you get more replacements, or should you charge him for some inspection cost and so on and so forth? Those things you sort out separately, that you do. When you're doing this, you'd be doing rectified inspection, or you'd be doing just standard rejection of the lot and returning the lot to the supplier. Now there is something that is also of interest to us. This is something that we would like to call the AQL leading up to what we call AOQ. Now suppose there is an inspection plan in effect. What I have here, I've got an inspection plan that is in effect, and I have here, I'm going to be doing that using a piece of paper there. My incoming parts, those are coming in lot size of N. N is the lot size of my incoming parts. That is the lot size, and it is coming in at a quality level P0. there is a certain probability of accepting this slot, and that probability is PA. PA at P0 level. And there is a certain chance of my rejecting that lot, and that is 1 minus PA is the probability of my rejecting the lot. How many items are here now? Let's take a look. Accepted lots, those are accepted at probability PA, and they are of quality P0. They are of quality P0 and the size is n. If you look at the number of items that come down this way, and if I actually work out the fraction of items, the number of items which are defective items in this stream, let's see how we work it out. On this side, on the average, if n items came in and I inspected them, I have n times PA. That is a chance of my going this way, and that's got a lot quality of P0. Now look at this side. I have here lots coming in, they are getting rejected, and they are, of course, all of them they have been rectified. So any items coming this way must all be 100% okay. On this side, unfortunately, I've drawn a sample and I've looked at the sample and I've replaced any defective items that I found in the sample. So therefore, what I have here, if you look at the quantity here, I have the average quality that is going out this way. That if I indicate by this quantity called AOQ, average outgoing quality this way, that is going to be PA multiplied by big N minus N multiplied by P0 divided by N. Let me explain to you what is going on here. N is the total number of parts flowing through the system. Once I've done rectification, I'm not returning anything to the supplier. So the rejected lots, they got rectified, they came along. I end up with some items here and I end up with some items here. But the total number of items coming this way is going to be N items. Now the ones that have been accepted, those have not been rectified. On this stream, on this side, I've removed all the defective items. But on this side, I did my sampling and I accepted them. Now, if there are any defectives in the little n samples, I removed those. I removed those defective items, and therefore those n times P0, those quantities have been removed. So the actual number of defectives going this way is going to be big N times P0 multiplied by PA minus N times P0 multiplied by PA. This is the number of defectives that I let go this way. Therefore, the fraction that actually comes out as the result of doing all this, AOQ at the outgoing level, this is at the average outgoing quality leaving the inspection booth, this area. This quantity turns out to be this quantity there. Now, a couple of things I would like to show now. Let's say I write down my AOQ figure as this. AOQ is equal to PA times N minus N multiplied by P0 divided by N. Now look at this quantity, and let's use a black pen. Look at this quantity now, and remember, alongside I've got my OC curve also. So my OC curve goes like this. I've got P here, I've got PA there, and the OC curve goes like this. It turns out when my little p is like 100%, that means everything is defective. When this is equal to 1, PA becomes 0. Therefore, the product of this and this, product of this is, it would be 0. So, this AOQ quantity, if I plotted the AOQ figure here now, AOQ, I have little p there, I have this little p equal to 1.0, that means everything is 100% defective. That's the worst possible thing, and here it is 0% defective. This p rises this way, so I get more and more defective parts as I go this way. That's lot quality. It turns out when little p is 0, when little p is 0, that means this quantity, if you look at it, when this is 0, no matter what this value is, AOQ is going to be 0. So, AOQ will have a 0 value there, and AOQ will have a value again 0, because PA becomes 0 at this point in time. So, even if this becomes 1, this is 0. Therefore, this is also a point that's for the AOQ quantity. Now, you look at all the other quantities here. This is a positive quantity, this is a positive quantity, this is a positive quantity, this subtraction, this difference is positive, this is also positive. Therefore, I've got only positive quantities there. This is of course a positive quantity. So, this curve between these two extremes must have some positive value there. This is positive, which actually says that if I am using the rectification scheme, at some point I will have the worst level of defects being passed, and this quantity can be determined, and also this quantity can be determined. Now, sometimes what happens, the consumers would like to tell you that there is a limit beyond which I cannot accept any kind of defects in the lots. There is a limit there, and this limit here is called AOQL, average outgoing quality limit. So, no matter what inspection scheme I am using, AOQL actually tells you the worst performance of that sampling plan. And many times consumers would like to specify this to you instead of giving you the what we call the AQL. Remember AQL was there? AQL. You might think that the consumer would be quite happy saying this to you. But the problem is sometimes we are also accepting lots which are at these quality levels, and because of that the consumer comes along and he says, I am going to give you a quantity called AOQL and please do not exceed that no matter what you do. Therefore, this is like another criteria by which I could design my sampling plans. I could of course use these things. I could use alpha, AQL, beta, RQL. I could use these constraints. To design my sampling plan. And the other, so this would be like one way. The other way would be to specify AOQL and then come up with a plan. I'm going to show you a method that uses this technique. I'm going to show you that. These are the same calculations which are just shown here in different schemes. And here is an example of AOQL, and this AOQL was specified by the consumer. Therefore, he gets now 8.2% defectives in his items. That's the worst quality level he is going to experience if the same sampling plan is applied again and again. And here again is the display of the AOQL. And here again is a display of the AOQL. And these curves can be drawn quite easily because I remember I have the formula. I have this formula here with me, and I have this OC curve with me, and with that I can calculate the different points on this and can determine what that AOQL quantity is. That's quite easy to determine. And of course, a double sampling plan would be an extension of what we've done so far. I take an initial sample. And I use the initial sample to come up with one kind of decision. I may be able to accept the lot, I may be able to reject the lot, and I may not be able to do that. When I do double sampling, what I do is I take a second sample. So I've taken a first sample, but it did not lead to a decision. I was stuck between these two decision points. Then I take a second sample, and based on the results of the first sample plus the second sample, I may decide to accept the lot or to reject the lot. This would be the way to do your double sampling plan. What the double sampling plan does beyond the single sampling plan is, the double sampling plan generally gives you a total lower, on the average it gives you fewer items to sample. That's one of the advantages of using the double sampling plan. So it gives you, generally speaking, a smaller total number of items. I could generalize that. I could go to multiple sampling plan, where the rules become slightly more complicated, but they follow essentially the same procedure. Take one sample, check it out if the number of defectives found in that sample are between the limits where you cannot really decide, you have to take another sample, and so on and so forth. You keep doing this. So you take the first sample, second sample, third sample, and so on. At some point in time, you are going to make a decision either to accept it or to reject it. Now, this may seem to be a little complicated to you. It turns out, yes, to implement these plans is somewhat of a complexity, because many times these procedures, they are not clearly understood by, they can understand, and they can, many of them, they follow the single sampling plan without any trouble at all. But the moment you bring in more stages of sampling, you go to the double sampling plan, the multiple sampling plan, and so on, then it does become a bit complicated to implement on the floor. But what you gain is, you have to do much fewer, you've got to do far fewer inspections. That's what you should be able to do. Then there is something beyond this which is called the sequential sampling plan. And I'm going to kind of just give you a hint of it. There what we do is, instead of taking like one lot of samples, which is like maybe your first sample will consist of these items, and then the second sample will consist of some more items there. You put them all together. That's your second item, second sample. I've got my first sample, then I've got my second sample, and so on. Then I try to decide something on the basis of that. The sequential sampling plan does something different. It again works with the same lot. The lot has been supplied to you. What you do is, you pick one item out of the lot, and you take a look at it, do the inspection, and record it as good or bad. Then you take a second item. Make sure the record is kept there. You take the second item out and inspect to see if it is good or bad. You do that. Then you take the third item. Again, so what you're doing is, you're doing one item at a time. You looked at the first item, you looked at the second item, you looked at the third item, and looked at the fourth item, and so on. You keep going like this till at some point you have to make a decision. You end up with a decision. And that goes like this. If I show you a curve there, it would be a lot easier for you to see. Notice here on the x-axis, I've got the number of items sampled. On the y-axis, I have plotted here the number of defectives found. In the sequential sampling plan, you start with one item and one item. And you've got two control limits here. One is the acceptance control limit. This is like a straight line, which has been drawn here as a curvy, stepwise kind of progress there. I'm going to show you the other one also in a minute. And then you got a rejection line also. If the trace of your sampling and results of the sampling, if they stay within these two limits, you continue to sample. The moment it goes either this way or this way, you decide to either accept the lot or to reject the lot. Let me show you what it looks like in real world. I've got a continuous line here, and this is the acceptance region. See, by doing sampling, I end up going here, I accept the lot. If by doing sequential sampling, I accept going somewhere here, at some point in time, I reject the lot. But if I keep going like this inside, it's always going to be rising. I keep doing sampling. But there's a theorem by Wald, which actually tells us, Abraham Wald, he told us you'll never end up going forever in this direction. You'll either end up going that way or you'll end up going this way. This is a very powerful method, and the formulas here, these lines are given as the straight equations, straight line equations, and their parameters are given by this expression here. You've got a rejection line, which is the lower line in the plot, and you've got an acceptance line, which is the upper line in the plot. So if we go back to the line there, This is the acceptance line. On this region, in this area, you will accept, you end up coming here like this point here, you will accept the lot. And if you end up going there, if you end up going here, you will end up rejecting the lot. Those are determined by this. And of course, the parameters to go into those equations, those are given here by K1, H1, S1 and H2. What is the advantage in doing this? The first thing is the OC curves turn out to be very similar to what we've done before. But the beauty is that you end up with far fewer items to sample. When you do one item at a time, when you keep picking one at a time, your decision is reached much earlier because this is a sequential likelihood. This is a sequential likelihood of finding so many defectives in a sequence. And that is something that's got much more power. So something like that you could quite easily do. And we'll follow through now with the design of the actual sampling plans. And I'll be showing you a couple of methods here. Thank you very much.